Hi, everyone. I am Dr. Jeremy Maurer at Missouri University of Science and Technology, and I want to talk to you about the role of fluid injection on earthquake size and dynamic rupture simulations on rough faults, which is work that I did principally while I was a PhD student at Stanford University, and then finishing up here at MS&T. So the hypotheses that we're considering, or really two end-member hypotheses that we're considering, have been proposed by previous studies. So the first one is related to work by Maurer and Barber, as well as others that have worked on this problem. And this hypothesis says that something about fluid injection controls the size of induced earthquakes that you get. So whether that's the injected volume, as in this case, is related to the maximum magnitude, or the spatial extent of pore pressure, either way, something about the fluid that you're injecting is limiting the size of ruptures. On the other hand, hypothesis number two, we're considering, the other end member, is that the largest size earthquake that you get is exactly what you would expect given the number of events that you observe at a given induced seismicity scenario, and the b-value that you observe consistent with Gutenberg-Richter. So this was published by Nick van der Elst in 2016, and he shows that for a lot of cases, the number of events or the largest size magnitude that you observe is simply what you would expect given the number of events that occurred. Now, these studies both considered a number of cases, a number of prior cases of induced seismicity. Since their publication, we've had a couple of interesting induced earthquakes. One was the Pohang, South Korea earthquake, which was actually well above the limits proposed by both of these models. And the other was the Finland earthquake, which happened during, again, a geothermal stimulation in Finland. And that was below both models. Either way, we have these two end-member hypotheses for what is controlling earthquake size. Is pore pressure controlling earthquake size? And so we want to investigate that. To do that, in this study, we're using a 2D dynamic rupture simulator called FDMAP. And you can see we published a paper about this in Geophysical Research Letters. Basically, we're using a 2D dynamic rupture simulator, so incorporating the effects that we think are active in dynamic rupture, such as off-fault plasticity, strong rate weakening friction, 1D band-limited self-similar faults embedded in the 2D medium. We're parameterizing the stress in that medium with the resolved normal and shear stresses on a planar fault of some orientation. The limitations of this model are that earthquakes are artificially nucleated. So unfortunately, we can't gradually increase the pore pressure until we get nucleation. We have to impose the pore pressure at the beginning, and we artificially initiate the rupture. We're looking at a couple different pore pressure models. One type of model is based on pore elastic diffusion in a homogeneous medium. We have two models, PM1, pressure model 1, and PM2. PM1 has a peak pressure of around 2 megapascals, and PM2, as you can see, is around 18 megapascal peak pressure. We also have a kind of what we're calling a boxcar type pressure model, where we have a high permeability channel across the fault, and that allows pore pressure to get very high inside that channel and is relatively low outside. So with those two models on planar faults, we see a very clear and consistent picture. At low stress levels, here's the background stress level on the x-axis, rupture length on the y-axis normalized by the fault length, and then the length scale over which pressure is decaying is shown with those gray bars. At low stress level, we see ruptures arrest. They don't rupture the full fault because the stress is too low. At high stress, so as we increase to very high background stress values, we see full fault ruptures. So the ruptures are able to rupture right through. In this case, both perturbed and unperturbed ruptures become full fault even if the perturbation is there. However, at some intermediate stress level, you can see that ruptures are arresting in the zone where the pore pressure is decaying to very small values. And if we look at individual examples of this, here's a particularly clear example where we have, this is pressure model 3, the boxcar type model. We have a rupture that begins. You see this initial pulse that's due to the initiation. And then the rupture is kind of propagating along. It reaches the edge of the perturbed zone where you can see the stress ratio, the resolved stress ratio changes, and then it dies away. Now this is consistent with kind of both hypotheses, depending on what stress regime we're in. So events at high and low background stress seem to be principally controlled by the pre-existing stress conditions. So even though we've perturbed the fault by adding pore pressure, at very, very low stress values, those events are just going to arrest. There's not enough stress to sustain them. Or conversely, at very high background stress levels, the presence of the pore pressure perturbation doesn't really matter in terms of the final size of the earthquake. It's going to just rupture right on through the pressure boundary. At some intermediate stress level, neither too high nor too low, ruptures are actually controlled by the spatial extent of pore pressure, and we saw that in the example rupture. This is on planar faults, but what happens when we introduce, and this is what we're interested in, rough faults? Well, we see a little bit more complicated of a picture. Here's a single example, and again, this is using the boxcar type pressure model. Without pore pressure, we essentially have a failed rupture, so the rupture doesn't even extend beyond the initiation region. With the added pore pressure from injection, we have, you can see a rupture which doesn't quite reach the edge of the perturbed zone on one side and ruptures through it on the other side. Why is the rupture stopping where it does? It's stopping because that's where the pre-existing stress, the pre-existing resolved stress on this rough fault was very, very low. And again, the absolute values of this is shear over normal stress on the fault. Those are going to look a little low depending on if you're used to thinking about friction as 0.6 or 0.7. This is because we have strong dynamic weakening on the faults and because we don't have good roughness resolution down to the length scale of slip. So we have very low resolved stress, pre-existing stress at these areas here, and that's where the rupture stops. It's not stopping because of the pore pressure, it's stopping because pre-existing stress is low. If we do this for many, many different kinds of different simulations, we have rough faults, so we can generate many stochastic realizations of faults. We can run this for many different pressure models for different stress levels and for different fault roughness values, alpha being a measure of fault roughness. We see a fairly consistent picture where in most cases, either the ruptures are not reaching the edge of the perturbed region or they're rupturing past it. And in high stress cases, they don't care about the pore pressure. They are very large ruptures and even in some cases rupture the whole fault. At low stress values, the ruptures tend to be small, although at low stress and low roughness, with a very strong pore pressure perturbation, ruptures can actually exceed the pressurized zone even at very low stress values. So what this is telling us is that the rough fault simulations are a little bit more complex than the planar fault simulations. For most ruptures, pre-existing stress conditions, and that includes stress heterogeneity from fault roughness, exert primary control over when they stop, which is consistent with hypothesis 2 that induced earthquakes behave essentially as tectonic earthquakes. On the other hand, at low stress, low roughness, and low pressure perturbations, some ruptures may be limited by the size of the pressurized region. This is consistent with hypothesis 1, that something about injection is limiting rupture size. And in this case, it's the spatial extent of pore pressure. What it's showing us is that there's this complex interaction between pore pressure from injection as well as the pre-existing stress conditions. And how those two things interact is what's going to determine what the largest earthquake size is.